static electricity can indeed be a safety concern when considering stray voltages and equipotential planes. Static electricity, at its core, represents an imbalance of electrical charges accumulating on the surface of various objects. When this imbalance escalates to a significant level, it can manifest as a sudden discharge in the form of a spark. This spark poses tangible risks. Firstly, it can serve as an ignition source for flammable materials present in the vicinity. Secondly, it has the potential to inflict damage on sensitive electronic equipment. While the National Electrical Code, or NEC, is a comprehensive set of guidelines for electrical installations, it doesn't explicitly address the issue of static electricity in the context of bonding hot and cold water pipes. The primary intent of bonding these water pipes is to establish a low impedance pathway for fault currents. This pathway serves a crucial role in mitigating the risk of electric shock to individuals who may come into contact with the plumbing system, and also in preventing potential damage to equipment connected to the electrical system. In essence, the bonding creates a safer electrical environment by ensuring that fault currents can be safely conducted back to the source, tripping circuit breakers or fuses and energizing the affected circuit. Despite the NEC silence on static electricity in this specific scenario, the practice of bonding hot and cold water pipes can indirectly contribute to reducing the accumulation of static charges. By providing a conductive path for these charges to dissipate, bonding helps to prevent the buildup of static electricity and subsequently lowers the likelihood of a spark discharge. The fundamental principle behind bonding and grounding, as outlined in the NEC, is to create an equipotential plane. This means ensuring that all conductive surfaces within a specific area are at approximately the same electrical potential. By minimizing potential differences, the risk of electric shock is significantly reduced. The NEC addresses bonding and grounding extensively throughout various articles, including Article 250, which is dedicated to grounding and bonding. This article provides detailed requirements for grounding electrode systems, equipment grounding conductors, and bonding jumpers. The NEC also addresses bonding requirements for specific equipment and locations, such as swimming pools, spas, and agricultural buildings. For example, Section 680.26 of the NEC provides specific requirements for bonding metal parts of swimming pools, including the pool reinforcing seal, metal fittings, and electrical equipment. The goal is to create an equipotential bonding grid around the pool to minimize the risk of electric shock to swimmers. Similarly, Section 547.9 addresses bonding requirements for agricultural buildings to protect livestock and personnel from electric shock hazard. The NEC emphasizes the importance of using listed or labeled bonding and grounding equipment. This ensures that the equipment has been tested and certified to meet specific safety standards. Proper installation of bonding and grounding systems is crucial for their effectiveness. The NEC provides detailed instructions on how to properly install grounding electrodes, connect grounding conductors, and make bonding connections. Improperly installed bonding and grounding systems can be ineffective and may even create additional hazards. Regular inspection and maintenance of bonding and grounding systems are also essential to ensure their continued effectiveness. The NEC recommends periodic inspections to check for loose connections, corrosion, and other signs of damage. Any deficiencies should be corrected promptly to maintain the integrity of the system. While the NEC doesn't specifically address static electricity concerning water pipe bonding, understanding the principles of static electricity and its potential hazards is essential for electrical safety. Static electricity is generated when there is an imbalance of electric charges on the surface of a material. This imbalance can occur due to various factors such as friction, contact and separation, or induction. When two objects with different static charges come into close proximity, a discharge can occur in the form of a spark. The severity of the spark depends on the amount of charge accumulated and the distance between the objects. Static electricity can pose several hazards in various environments. In flammable environments, a static spark can ignite flammable gases, liquids, or dust, leading to explosions or fires. In electronic manufacturing facilities, static discharge can damage sensitive electronic components, causing equipment malfunctions or failures. In healthcare settings, static electricity can interfere with the operation of medical equipment or pose a risk to patients with implanted medical devices. To mitigate the risks associated with static electricity, various control measures can be implemented. Grounding is one of the most effective methods of static control. By connecting conductive objects to ground, static charges can be safely dissipated, preventing the buildup of static electricity. Another common method is to use anti-static materials such as anti-static sprays, mats, and wrist straps. These materials help to reduce the generation and accumulation of static charges. Humidity control can also play a role in static control. Higher humidity levels increase the conductivity of air, allowing static charges to dissipate more easily. In some cases, ionization can be used to neutralize static charges. Ionizers generate positive and negative ions in the air, which can attract and neutralize static charges on surfaces. In summary, while the NEC doesn't explicitly address static electricity in relation to water pipe bonding, the principles of bonding and grounding, as outlined in the NEC, can indirectly help to reduce static electricity and its associated hazards. Understanding static electricity, its potential hazards, and effective control measures is essential for maintaining electrical safety in various environments. The NEC provides a comprehensive framework for electrical installations, including bonding and grounding requirements to minimize the risk of electric shock and other electrical hazards. The NEC is updated every 3 years to reflect changes in technology and industry practices. It is important for electricians and other electrical professionals to stay up to date with the latest edition of the NEC to ensure that their work complies with current safety standards. The NEC is not a substitute for proper training and experience. Electricians and other electrical professionals should receive adequate training in electrical safety and installation practices. They should also have sufficient experience to be able to identify and address potential hazards. Electrical work should only be performed by qualified individuals who are familiar with the NEC and other applicable safety standards. Improper electrical work can be dangerous and may result in electric shock, fire, or other hazards. If you are not qualified to perform electrical work, you should hire a licensed electrician to do the work for you. When working with electricity, it is important to take precautions to protect yourself from electric shock. Always to energize circuits before working on them. Use insulated tools and equipment. Wear appropriate personal protective equipment, such as gloves and safety glasses. If you are unsure about how to perform a task safely, consult with a qualified electrician. Electricity is a powerful force that can be dangerous if not handled properly. By following safety precautions and complying with the NEC, you can minimize the risk of electric shock and other electrical hazards. The NEC also covers other types of wiring. Article 310 covers conductors for general wiring. It specifies requirements for conductor insulation, ampacity, and installation. The NEC also covers wiring methods for different types of occupancies. For example, Article 517 covers healthcare facilities. It specifies requirements for electrical systems in hospitals, nursing homes, and other healthcare facilities. The NEC also covers wiring methods for hazardous locations. Article 500 covers hazardous locations. It specifies requirements for electrical equipment and wiring in areas where there is a risk of explosion or fire due to flammable gases, vapors, or dusts. The NEC also covers wiring methods for special equipment. For example, Article 620 covers elevators. It specifies requirements for electrical systems in elevators, dumbwaiters, and escalators. The NEC also covers wiring methods for renewable energy systems. Article 690 covers solar photovoltaic systems. It specifies requirements for electrical systems that generate electricity from sunlight. The NEC also covers wiring methods for energy storage systems. Article 706 covers energy storage systems. It specifies requirements for electrical systems that store energy, such as batteries. The NEC also covers wiring methods for electric vehicles. Article 625 covers electric vehicle charging systems. It specifies requirements for electrical systems that charge electric vehicles. The NEC is a complex document that is constantly evolving. It is important for electrical professionals to stay up to date with the latest edition of the NEC to ensure that their work complies with current safety standards. Stray voltage, also known as neutral to earth voltage, is a phenomenon where a small voltage exists between the grounded neutral conductor and the earth or other grounded objects. This voltage is typically very low, often less than 10 volts, but it can sometimes be higher. Stray voltage can be caused by a variety of factors, including imbalances in the electrical system, faulty wiring, and improper grounding. In agricultural settings, stray voltage can be a particular concern as it can affect livestock. Animals may experience discomfort or stress if they come into contact with stray voltage, which can lead to reduced milk production, weight loss, and other health problems. To mitigate stray voltage in agricultural settings, various measures can be taken, such as improving grounding systems, balancing electrical loads, and installing specialized equipment to filter or block stray voltage. Equipotential planes are areas where all conductive surfaces are bonded together to create a uniform electrical potential. This helps to minimize voltage differences and reduce the risk of electric shock. Equipotential planes are commonly used in swimming pools, spas, and other areas where people may be in contact with water and electrical equipment. The NEC requires the establishment of equipotential planes in these areas to protect people from electric shock hazards. Bonding is the process of connecting conductive objects together to create a continuous electrical path. Bonding helps to ensure that all conductive surfaces are at the same electrical potential, reducing the risk of electric shock. The NEC requires bonding of various metal parts in electrical systems, including metal conduits, enclosures, and equipment grounding conductors. Grounding is the process of connecting an electrical system to the earth. Grounding provides a path for fault currents to flow back to the source, tripping circuit breakers or fuses and energizing the affected circuit. The NEC requires grounding of electrical systems to protect people and equipment from electrical hazards. The grounding electrode system is the primary means of connecting an electrical system to the earth. The NEC specifies various types of grounding electrodes, including ground rods, ground plates, and metal underground water pipes. The grounding electrode system must be properly installed and maintained to ensure its effectiveness. The equipment grounding conductor is a conductor that connects the non-current carrying metal parts of electrical equipment to the grounding electrode system. The equipment grounding conductor provides a path for fault currents to flow back to the source, tripping circuit breakers or fuses and energizing the affected circuit. The NEC requires the use of equipment grounding conductors in most electrical circuits. Ground fault circuit interrupters, or GFCIs, are devices that protect people from electric shock by detecting ground faults and interrupting the circuit. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas, to protect people from electric shock hazards. Arc fault circuit interrupters, or FSIs, are devices that protect against fires caused by arcing faults. An arcing fault is an unintentional electrical discharge that can generate heat and ignite nearby combustible materials. FSIs are required in many locations, including bedrooms, to protect against fire hazards. Surge protective devices, or SVDs, are devices that protect electrical equipment from voltage surges. Voltage surges are transient overvoltage conditions that can damage or destroy electronic equipment. SVD are installed in electrical panels and other locations to protect sensitive equipment from voltage surges. Electrical safety is a critical concern in all environments. By following the NEC and other applicable safety standards, and by taking appropriate precautions, you can minimize the risk of electric shock, fire, and other electrical hazards. Remember to always consult with a qualified electrician for any electrical work or questions. The information provided here is for general educational purposes only and should not be considered a substitute for professional electrical advice.